Right. Prop 36 says parallelograms which are on equal bases and in the same parallels are equal to one another. So this is the one I would claim that really establishes that the area of a parallelogram is base times height, because it's just saying that if you take any parallelograms at all where they have equal bases and then they're falling between the same two parallels, in other words, they have the same height, then the area of those two parallelograms is the same. And Prop 35 was really similar to this, but this kind of like generalizes to any two parallelograms with equal bases, rather than Prop 35 was talking about two parallelograms that have the exact same base. So here they don't have the same bases at all, but we are saying that the bases are equal. So yeah, assume that we have two parallelograms, ABCD and EFGH. Both of them are falling between the parallels AH and BG, such that BC is equal to FG. So what we want to prove then is that these two parallelograms are they have the same area, or the way that it's stated in the proposition is that they're equal, which again doesn't mean that they're congruent, it means they've got the same area. All right, so proof, and maybe I'll just say, just to kind of write it out, we're given that BC equals FG, and that AH is parallel to BG. So that's kind of the setup. Now we need to prove that the parallelograms are the same. Well, how do we do that? The first step is we're going to join BE and CH. So in other words, we're kind of joining the bottom base of ABCD to the top base of EFGH. So I'll do that, and I'll do it with a dotted line just so that it's kind of obvious, because it's easy to lose the original parallelograms. Oops, needs to be up a little bit. It's easy to lose the original parallelograms when you start putting in too many lines. So there's BE. Here comes CH. Yeah, and if you'd like, if you're kind of practicing any of this, this is a great place to stop. That's just sort of like a hint for you. See if you can carry it the rest of the way. That's kind of like the big step that needs to be done in order to solve this thing out. All right, so we join BE and CH. Well, what do we have? Well, we know that BC is going to be equal to EH, and I think that should be justified. Let's see here. How shall I say? Right. Actually, maybe that's, oops, no, that needs to be deduced. That BC is equal to EH. That is where we're heading. So we know that BC is equal to FG. We're given that. Then we can say, since FG equals EH, and this is stated in the book, or in the elements. Let me just read it, but it's not justified, and I think that it should be justified. Euclid says, since BC is equal to FG, which is what we're given, while FG is equal to EH, BC is also equal to EH. So that's what we want to prove, and the intermediary step is this right here, FG equals EH, but we're not actually given that. So I think that needs to be justified, and I believe that was Prop 34, because Prop 34 is the one that says, in parallelogramic areas, the opposite sides and angles are equal to one another. So yeah, I think that we should state that. That's where this comes from, because we aren't given that just straight away, the way that I see it. But then if BC equals FG and FG equals EH, it follows that BC equals EH. And of course that's justified. maybe it was like, maybe they made a little mistake because they justified common notion 1 there, whereas previously in this line of reasoning they just sort of stopped justifying common notion 1, and they didn't justify prop 34. So I wonder if they just maybe meant to put prop 34 there where they wrote common notion 1. It's no big deal. Right. So yeah, BC is equal to EH. But we also know that since BC falls on BG, EH falls on AH, it follows that BC is parallel to EH. So, let's see. So it follows BC is equal to EH, and I'll just kind of put this also. BC is parallel to EH. Then we know that, let's see, I'll just read the line because it's really just a proposition. Euclid says, but straight lines joining equal and parallel straight lines, which is what we have. So BC equals EH and BC is parallel to EH. So now we're talking about the lines that are joining them. So namely BE and CH. Straight lines joining equal and parallel straight lines in the same directions are equal and parallel. So we get that BE equals CH and BE parallel to CH. And that was by prop, which one was it? Prop 33. That gives us that. And then the next line is, therefore, EBCH is a parallelogram. And that comes from, that's justified under prop 34 again, which, right, is the one that we already kind of talked about, that's in parallelogramic areas, the opposite sides and angles are equal to one another, and the diameter bisects the areas. So that's saying that if a quadrilateral is a parallelogram, then the areas, the opposite sides and angles are equal to one another. So it's kind of like an implication or reverse implication, because here we have sort of the other way, that BE equals CH, so the sides are opposite each other, are equal, and they're also parallel. Sorry, somebody's going up the street super loud. It's really obnoxious. Right. So we kind of get that if that's the case, then this must be a parallelogram, because otherwise, if it was not a parallelogram, this wouldn't hold. So thus, EBCH is a parallelogram. Right. Does that even really need to be justified? So I guess I should write that out. Now that I'm thinking about it, does that need to be justified? I don't know. It's justified in the book, but I sort of feel like maybe that actually, now that I'm thinking about it, that actually kind of follows from the definitions, right? Because all that we're saying is that opposite sides are parallel. We established that BE is parallel to CH, and we already know that BC is parallel to EH, so yeah, this ends up being a parallelogram. Now that I'm thinking about it, I'm not really sure that even really needs a proposition to justify that. Maybe I'm overlooking a detail, because I think that's sort of built into the definition, although at the same time, Euclid doesn't actually outright define a parallelogram. It's sort of just like it's not in the formal definitions at the start of the book. It's kind of just assumed that a parallelogram is like, it's a quadrilateral where the opposite sides are parallel. So maybe that's why the proposition is put in there. I don't know. It seems a little bit shaky, but it definitely seems logically correct. So yeah, EBCH is a parallelogram. Well, notice then, I'll say, since ABCD and EBCH share a base, namely BC, and fall between the same parallels, we have a proposition that says something about that. When two, let's see, has the same base, same parallels with it. For that reason, they're actually equal to each other, and that was prop 35, right? The one that we just did. That parallelograms on the same base and the same parallels are equal to each other. So because of that, ABCD equals EBCH, which was prop 35. That's the same guy. He's back. He wants to be on the video again. I'm sure that my mic is picking that up. I should close my window. He's just going to ride around the block. I guess he's got nothing better to do. What else do we have? Similarly, we have that EBCH and EFGH share base EH. And again, fall between the same parallels. Whoops. Same. We get that EBCH is also equal to EFGH. By the same prop. It's the exact same reasoning. It's just sort of like looking at it from the other side now. EBCH equals EFGH. So we get the conclusion. ABCD equals EFGH. Yep. QED, therefore, etc.